Hey, welcome to this presentation on counting. I think you're going to get excited about this stuff. What's counting anyway? Do you know how to count? You think you do, don't you? Look at this. So you think you can count. But maybe it isn't that easy. Let's have a look and see what we're talking about in this really intriguing area of mathematics. Counting, here we are, is the action of finding the number of elements of a finite set of objects, or number of elements in a finite set. Finite, it's ending. It has a beginning and an end, not like the real number set, for example. Okay, so here, I come across the top left screen of here, and we've got some blocks that you started using when you were counting. They've all got numbers on them. So it's easy to count up how many there are. And what about over here? Can you count to 100? I bet you can. But what about 1,000 or 1,000,000? Now maybe counting could get difficult if that finite set up here, finite set, was very, very large. What about down here? Do you know some tricks to do with counting? I think you do. Here are bundles of 5, like you count by 5. By 5s. 1 5 is 5, 2 5s are 10, and so on. And I think you might have used that. Come along here in your junior burger days learning statistics. Counting up or tallying. Okay, here we are. We're counting something up and we're putting a straight for everyone there is. Uh-oh, that's going to get hard to add all those up. So every fifth one, we lay one down. Have you seen that before? So we make bundles of 5. Instead of doing multiple addition down here, instead of trying to add all those up, multiple addition. Is there a quick way of doing many additions? Well, there's a word for that, isn't it? Isn't there? For real numbers, at least, multiple addition is multiplication. Multiplication, multiple addition. Okay, do you realise that when you put these bundles of 5 up here, you've got 5 lots of 5. And that in maths is 5 times 5. Multiple addition is 25. So there's a trick, a couple of little tricks there, of bundling the tallies up and then using multiple addition or multiplication. You know a couple of tricks about counting already. What about this one over here? Can you count up the number of balloons here easily? Well, let's look at it. 1 row of 8, 2 rows of 8, 3 rows of 8, 4 rows of 8, 5 rows of 8. So we've got 5 lots of 8, which equals 5 times 8 is 40. What others have we got? Well, we've got 1, 2, 3, 4, 5, 6, 7 there. So the total will be 40 plus 7. Down the bottom, 1, 2, 3, 4, plus 4 will be 51. So this multiplication idea can shorten a lot of counting that we might do. What about these two? Gee, you can go and tell people you do a lot of high-powered maths if you could understand what's going on there. That looks complicated. Well, it's not really. You're going to find out how it all develops in this exciting presentation. What about this thing here? That looks like an exclamation mark. And they're all over the place. Does this mean these little letters, these pronumerals, are all excited? Like here, so you think you can count? No, different meaning for the exclamation mark, I think. We're going to find what that symbol means in maths in this very presentation. So come on down and let's get started. Here's the question. What happens when finite is a really large number in that set, that finite set that you're counting up? What if it's really, really large? Do you know that people, if they can't sleep, count sheep jumping over a fence? So imagine sheep are jumping over the fence, and if they keep going, it makes them fall asleep. Like 1, 2, 3, 4, 5, 6. I'm falling asleep. I can't fall asleep now. I've got to get on with the presentation. So you could fall asleep counting a large number, couldn't you? What about this problem I've got here for you? You might not be aware, but there is a game called Cross Lotto, where there are 45 balls numbered 1 to 45. They roll around in a container, and one pops out, or you take one out at random every so often until you've got 6. And you win the game if you can list the correct 6 balls that are picked out. Now, that sounds like there would be a lot of different combinations of 6 balls. Could you count those up? How would you do it? Come down here. I started, but I gave up. How many balls are here? Oh, well, let's use multiplication. There are 1, 2, 3, 4, 5 rows, 5 lots of, and how many in each row? Well, I've labelled them there 1 to 9. I started doing this. 5 times 9 is 45. So there are 45 balls there. And why did I give up? I gave up because I tried to list the possibilities. I thought, well, the 6 balls could be the first 6 numbers. Not very likely, I guess, out of 45, but that could be the first one. And then what's another possible combination? It could be 7. And then it could be, hey, I don't think I can do this. I'm going to fall asleep doing this. It's going to be a lot, isn't it? Because that's just one bundle of 6, and then I'm changing it slightly. Oh, this is going to take forever. So, is there a better way? How many do you reckon there would be here? 1,000, 2,000, 5,000, 1,000,000, 2,000,000? How many possibilities? Hey, that's the interesting area in mathematics called counting and counting techniques. Come on down and let's start the journey. Okay, here we are. If you have 3 different pairs of jeans and 2 different pairs of shoes, list the number of ways you could dress yourself. Do you want to have a go at that? Pause the presentation, have a go. Well, I'm going to come back now. I'm going to say I have jeans 1, jeans 2, and jeans 3. And I'm going to have pairs of shoes 1 and pairs of shoes 2. How many ways can I dress myself? Well, shall we start with the shoes? Oh, no, can't start with the shoes. You got to pull your jeans on first, because otherwise you can't pull them over your shoes, mate. Okay, we'll start with jeans. So we've got jean 1 with pair of shoes 1, or jean 1 with pair of shoes 2. Then we've got jean 2 with pair of shoes 1, jean 2 with pair of shoes 2, jean 3 pair of shoes 1, jean 3 pair of shoes 2. I reckon that's all the arrangements we can do, and there are 6 of them. So did you get that answer? Okay, so this is going back to listing and adding them all up, or counting them all. Well, we said that wouldn't work too well with our Lotto problem, so we might have to work harder on that. Let's do something else now. If we make the problem bigger, we now have 4 different shirts or tops in addition to those clothes. In how many ways can you dress yourself? All right, so you could have jean 1, pair 1, and top 1. Or you could have jean 1, pair 1, and top 2. Jean 1, pair 1, top 3. We got 4 tops, jean 1, this is getting boring, top 4. So we have done one of our arrangements before and put them with 4 tops. Now we'll do the next one. Jean 1, pair 1, top. We've got to get rid of that. That's jean 1, pair 2, isn't it? Top 1, jean 1, pair 2, top 2. You see, I've got a system here. Counting needs a system or a structure. Very mathematical. Counting is, of course, working with numbers. Here we are. What have I done? I've made 4 out of my initial arrangement. So if we keep going, can you see what will happen? We had 6 different arrangements up the top there, and each one will now have, not be 1, but it will be 4. So we'll have 6 lots of 4, which will be 6 times 4 is 24. How about that? Do you get the idea? We want to give this away here. We don't want to do this. We want to use mathematics. How powerful is that? Let's keep going and see if we can devise a method. Devise some method which you could use to count up the number of possibilities in situations like these without actually listing all the possibilities. Well, you could think of the old tree diagram, couldn't you? Back in probability, Junior Berger probability, where'd we start? Gene 1, and we could go to pair 1 or pair 2, and then we had 4 tops, and here 4 tops, and so on. So you could do that and then count them all up, but we want a quicker method. So we had how many genes here? Gene 2. So we had genes times pairs of shoes. Oops, we had 3 genes. We had 3 by 2 by 4. So it looks like using a product for each different category, that's jeans, pairs of shoes, and tops, that would work. That looks like that would work. What about this? Use a method to count the number of ways of constructing a car. You have the body, choose from 6 different motors, 3 different types of wheels, and 5 different colours of paint. Let's try to use it. 6 motors would go with 3 different wheels and 5 different colours of paint. Do you agree? That would be 90 ways. Okay. What are we doing? Hey, this is coming along nicely, isn't it? No listing needed now. So let's take a look at this method. This is called the box method because we put it in a box. And the box has different sections for the categories that we're trying to look at the variation in, where we've got different possibilities. So the numbers are the number of different choices we can make in each of those categories. And we use what we've just established, the product principle. Okay, so this is called the product principle of working out all the possible arrangements. It's sometimes, we'll develop this later in the presentation, sometimes called the permutation. A permutation, a mutation, a changing around with different orders involved here. Okay, so we'll build that later on. Gee, we're learning a bit, and can you see that you are devising this in a way all by yourself? As a budding young mathematician, I want you to get excited about the fact that you can develop ideas for yourself. Okay, come up here now and show how to use the box method to count the number of possible different number plates in South Australia. If we start with that plate, it starts with the letter S, then there's 3 numbers, and then there are 3 more letters. And it could go right up to Z or Z, and the biggest single number you can have there, single digit number, is 9, and then any letter of the alphabet up to Z or Z again. Okay, pause the presentation and see if you can work that out. All right, coming back. What do we got? We're going to have a box here, and there are, 7 positions? 1, 2, 3, 4, 5, 6. Put one on the end there, 7. The first one starts with S and goes through to Z for that position. Let's do it. S, T, U, V, W, X, Y, Z. 8. I didn't list them, but I did count them up on my fingers. Oh, that's pretty crude. Here we are. It can go from 0 to 9. I know 1 to 9 is 9 numbers. And a 0 would be 10 different numbers we can put in here, single digit numbers for each of those spots. And then on the end it goes from A to Z or Z. So there are 26 letters in the alphabet. Each of those would have 26 different possibilities there. So what is it? What is the total number of different plates? So putting a little setting out down here would be 8 by 10 by 10 using the product principle or the permutation of these objects. There we have it. And so if you did that on the calculator, I think you get 8, 1, 4, 5. I think, hang on, let's have a look. 0, 6, 0. Okay. No, that's the wrong answer. That's the answer to a problem later on. Our answer here is this one, sorry. 140608000. Gives you an idea of how many cars you could register using that system before you might have to change the system. You might know that various places around the world have to change their system from time to time to accommodate the number of vehicles. But that's the answer there. Sorry I gave you the wrong answer before, because that's an answer to that cross lotto problem. Okay, let's go down, and here's some for you to try. These are permutation problems. You're going to use the product principle and a box for the moment. Okay, and how many ways can we fill two seats using 4 students? List the actual seating arrangements if the students were A, B, C, and D. All right, pause the presentation and see if you're going to have a go at this one. All right, coming back now, we have 2 seats, so we have 2 categories. Are they different? Yep, let's say this is a window seat. And some students want to sit at the window and look out all the lesson and not listen to the teacher. Oh, that's sad. That's bad student, bad student. All right, now do you want to be the bad student? Sit at the window, 4. Could be 1 of 4. And when somebody sits there, you've only got 3 other students to fit in there. So the total ways of doing this is 4 by 3 is 12. Now, can we list those 12 different ways of seating 4 students? Let's have a look. We could have AB, and BA would be different because that's a different window seat person. And then you could have what? A with C, C with A with D, D with A. But can you see what I'm doing? I'm listing bundles of 2. And this is what I would have had to do if we hadn't found or discovered the product principle. I like to think of maths as out there somewhere, and we're discovering various aspects of it. The patterns in the world that, who was it, Pythagoras, said the world is number. I think there's a lot of maths out there we're discovering. Okay, anyway, so that's A with all its mates, and now it's B with C, and its rearranged order. There's another pair, and then B with D, and D with B, the other way around, right? How are we going here? And that's starting with A in the window seat, and then with B with different arrangements. And now we could have just C and D together, and DC. Have we got them all? 1, 2, 3, 4, 5, 6 lots of 2 is 12. Yes, that checks. Okay. Did you get that? Can you see that we want to remove this approach? It's too time consuming. You could leave stuff out. This is the way to go, the permutation method via using a box and the product principle. What about this little problem here? We now have 3 seats, excuse me. In how many ways can we seat 3 students? Oh, they're all going to be sat down now. Nobody missing out. So we have 3 positions and 3 students. How many ways can you fill the first seat? 3. We've used 1 there, there's 2, then there's 1. So the number of ways would be 3 by 2 by 1, which would be 6. All of them are seated. 3 students, there's 6 of them. A, B, C, A, C, B, B, A, C. Remember, the different orders mean something in this problem, so these have to be counted each as separate possibilities, and these 2 as well, even though it's the same 3 students. And what about the last one? Start with C. Can you see the system? Starting with A, starting with B, starting with C, and they are the 6, which are different orders of the same 3 students. All right. How did you go? Let's go down here. I want you to repeat the process for 5 students and 5 seats, but do not list the different arrangements. There's too many. Okay, pause it and have a go. Right, here we are, 5 students and 5 seats. So 1, hang on, let's come out here a bit. 2, 3, 4, 5. There's our 5 seats, and we've got 5 students. How many ways can you fill the first one? 5. One person sat down, here 4 left. Then 3, then 2, then 1. So the number of ways is the product principle, the permutation, if you like, of these 5 people taken 5 at a time. How many different ways can you list them? There we are. And so number of ways is 20, times 3 is 60, times 2 is 120. Now you know why I didn't want you to go back to listing, because 5 students and 5 seats is a big list. There's 5 students. Then we could do what? I don't know, you've got to rearrange them. Oh, see what I've done there, and keep going. 120 times. Can you see that maybe you couldn't count before we started this as well as you thought you could? Because sometimes the listing has to have a system and it gets very long. The finite set could get very big, and you also could mess up the number of possibilities through not being able to list accurately. Oh, we're coming along. Do you agree? Come up here now. There's a mathematical expression called the factorial, and it is defined as this. How would you describe that? Have a think about that. You're starting with a number, you're taking one away because somebody sat down, you haven't got that person to use in the next seat, and then the next person, right down until everybody is seated. So the factorial means the product of an integer with every integer between itself and 1. So the factorial means all the integers between itself and 1 are factors, if you like, of this number. The factorial, the ultimate factorial. And there it is. There's the exclamation mark. It didn't mean a surprised n. It means you're using all the seats for all the people, and therefore you're going to multiply by every number between the number, 1 less, every integer, down to 1. Do you get it? That saves us using these clumsy-looking boxes sometimes. You must have thought, hey, can we do better with maths than just drawing boxes? And that's an excitement coming up further along now. So here, what would this be? This is 3 by 2 by 1. So it is a surprised n, 3 factorial. And this is 5 by 4 by 3 by 2 by 1. And so it is 5 factorial. And you can see from before what it means. Come down, let's have a closer look at it. How would you describe what the factorial gives in terms of n objects? You take all n objects, and what do you produce? These might be some hints down here for you. N factorial gives the number of ways. Now pause the presentation and think about what's going on this screen and see if you can complete the sentence. All right, n factorial gives the number of ways. Well, let's go to the hints here. Here we've got 3 items all chosen. And what would you say? They're the same 3 items, but they are in different orders. Different orders. And over here, this looks like we had, what, A, B, C, D. We had 4 items for 3 positions only. 3 positions. And so it's not the factorial. It would be 4, 3, 2. But what do you notice? There's only 4 possible selections, or 4 possible selections of 3 positions out of 4. But then all of these are just the different orders of those selections. The different orders. And you've got 3 items. How many different orders are there? 6. So there's 6 different orders of 3 items. So there is a factorial hidden in there. these are the ways in which you can select 3 different students for 4 seats, right? Out of 3 seats, 4 students to fill 3 seats, right? 4 filling 3, and these are the different selections. But then you've got these different orders you can put them in, okay? So there are 6 different orders for 3 students, so it's 3 factorial. So n factorial gives a number of ways of ordering n objects, putting n objects in an order. Okay, so that's not a bad way of thinking about it. That's a handy way. If you say, well, you're going to line all these people up and there are 10 of them, how many different ways can you line them up in different orders? That is 10 factorial. Quickly now, isn't it? You can do that quickly. No boxes, no listing. Wow, let's keep going. We're getting some skills here. Here are some questions for you to try. In how many ways can we fill 3 seats using 5 students? Pause the presentation and have a go. All right, let's have a look now. Got 5 students, 1 is seated, you've got 4 left, then 3 in the final position. So you're not using all of them. So it's 5 by 4 by 3, which is 60 different ways. I should put number of ways. Keep our mathematics orderly. 5 by 4 by 3 is 60 ways. All right, so what happened there? What's this got to do with that? You didn't go from 5 right down to 1. We went 5, 4, 3. I'm going to develop this for you in a minute. Let's keep going. So this was a permutation of 5 students taken 3 at a time via the box method. Okay, so come on down here. In how many ways can we fill 4 seats using 7 students? 4 seats, let's do it. 1, 2, 3, 4 students. 4 seats using 7 students. 7 by 6 by 5 by 4. The number of ways, same approach, the permutation of 7 students taken 4 at a time. 7 by 6 by 5 by 4. Okay, this is 42 times 5 is 210, times 4 is 840. Okay, the number of ways is 840. Do you agree with that? Okay, so again, we haven't done it, have we? We've started with n, but we didn't get right down to 1. So it is not equal to n factorial or 7 factorial. It's not equal to that. Okay, can we write a better explanation of this process without the boxes? That box method seems very unusual for maths, not very formula-like, not very neat, if you like. If we're arranging R students from n, what is the formal statement of the required product? Pause the presentation and I want you to see if you can write that product. It doesn't go down to 1. Okay, pause it and have a go. All right, let's start up again. It went from n to n take 1, n take 2, and where did it end up? Let's see if we can work it out. We had 7 students, n was 7, and R was, hang on, let's just go back up. What was R? R was 4, and we went 7 by 6 by 5 by 4. So in terms of n, it started at 7 and it went down to the number down here, which was 4. How do you get 4 from this? What are we going to do? It's n is 7, 6, 5, and 4. So we want an expression here for that 4 in terms of how many do we take away from n to get the number 4. This would have been n take 3. R. So where does it stop? It stops at n take R, 7 take 4, plus 1. Okay, so n take R, 7 take 4 is 3, plus 1 is 4. Do you see that? That's complicated. Or you could say it goes down to R, but really it's gone n take 1, n take 2, and n take R plus 1. Just check it. This is 7, 6, 5. 7 take 4 is 3 plus 1 is 4. This was the trick. To write a formula which you could easily see being 1 integer less as we went down. You might have to check that and go back over it and make sure you can see what we're doing. All right, maybe check with your teacher. Okay, so come up here. Can we find a formula which will be more easily programmable on a calculator or a computer, or just a neater way of representing this? That's what we want now. You can see where we're headed? Not listing, not counting, 1, 2, 3, etc. Now we want the box method, but we don't want boxes in maths. We'd like a nice formula. So have a look at this. Now, do you think you're good enough to write the top line out with a few dots in it as well? That's not easily programmable. And n take R with a few dots in it, n take R factorial, what would that look like? And if you write one over the other, can you cancel? So see if you can write n factorial, n times n take 1, etc., and n take R factorial, and then cancel some terms out. All right, pause the presentation and have a go. Here we are back again. Let's write it down here now. n take 1, n take 2 goes right down to 1. It's a big one. N take R, oh, it starts somewhere down here. N take R by n take R take another 1, right down to 1. So what would the term be in front of this one? So here, let's say this top factorial would contain all of this, wouldn't it? Down from n take R take 1, down to 1. That would all cancel. So what would be the term before the n take R term out there? Hey, it'd be n take R plus 1. Wouldn't it? 1 more than n take R. Wow, we just found it. N by n take 1 by n take 2 down to n take R plus 1. That's what we said was what? The factorial, the product that we wanted when you have the permutation of n objects taken R at a time, at R per time. That was a permutation in that box. Went down to n take R plus 1. So we don't need a box anymore. How exciting is that? That formula will give us that, what? Stopped product, if you like. That product has been stopped from going down to 1. So we could write it as 1 factorial over the other, so that we take out that from n factorial and we end up with this halted or stopped product. Hey, this has really gone very quickly, hasn't it? So now you understand this as replacing the box for the permutation of n objects taken R at a time. Wow, you're getting good at maths. Let's go down now and have a look. And here's the formal statement. P and R, the permutation of n objects taken R at a time. And this is one of the reasons we tend to write PR for probability. So it's not confused with P in counting land for permutations. And we have our nice looking formula. And this is called the permutation of n objects taken R at a time, and it replaces the box. Okay. It can be used without a box to calculate the number of ways of choosing R objects from n distinct different objects, and place them in all possible orders. Now that's very, very important that you realise that's what we did every time. Remember the ABC, the ACB. When we use the box, it's all the different orders. So we have to watch using that approach if we don't want to count the people as different from each other. In other words, if you only have 2 seats and it doesn't really matter which way round they sit, not next to the window. So some problems don't want you to count different orders as different possibilities. But this method says, hidden within it, all the possibilities, it includes those that are just different arrangements of the items taken. So we'll work on that. Come down now and let's have a look. This is important. You can program a graphics calculator to do this MPR. And notice how the calculator doesn't do this. You have to enter the N, then hit the button P, and then enter R. And there's another little dude that's in the same window, and also in the same window on all the graphics calculators, you push run and options and then probability, because counting, of course, is intimately connected with probability, because probability is what? Your chances of getting what you want, NS or NE, the number of items making up your event, divided by the number of total population of sample results, NS maybe. So we've got to count up how many things. So counting is intimately related to probability. And so that's why it's in the probability section on the calculator. And also R factorial or X factorial, and it depends on the calculator you're using, is also there. So you can do this calculation quite quickly without multiplying right down to 1. Those things are programmed on the calculator. So that's handy. Can you see how quickly we've moved on in this counting area of mathematics? Come down now. But can we answer the cross Lotto question? In how many ways can you use or select 6 numbers from 45? And don't do this. Don't race in and put, I'm going to race in, P45, 6. Off to the calculator, I'm going to work it out. Did I make a mistake? Yes, I did, because that would give me all the different arrangements of the same 6 numbers. The permutation will rearrange the 6 numbers in a different order, and you can't count those as different possibilities, because Cross Lotto only wants you to name the balls in any order. Don't count them as different possibilities. If that came out in that order, that wins. So the next order would be what? 5, 4, 6, whatever, changing them around. And permutations counts that as a different order. So there aren't that many possibilities. You don't want to count all those as just different orders. So can you see, we still can't answer the Cross Lotto question. So we're going to have to do some more work. Come on down now and have a look. Our permutation formula gave us a number of possibilities of choosing R from N, the permutation of N objects taken R at a time, and putting them in all different orders. It doesn't matter in Cross Lotto what the order is in which the balls are drawn. So you've got too many possibilities. Let's see if we can do something with that. So when we chose 2 students from 4 at the very beginning, there were 12 possible arrangements. These involved some which were just different orders of the same 2 students. How many were there? So A, B and BA, A, C and CA, A, D and DA, B, C and BD, BC and CB, BD and DB, CD and DC. All right, so we don't want the red ones. How many were there? Well, we've doubled, haven't we? Everything was times by 2 because there were 2 orders for 2 items. So if you're doing our Cross Lotto problem, we want to remove all of those from the big total, which is just different orders. Because we just want R selected from N in any order. It just depends on the batch of R that we get, whether we're going to win this. Okay, so there were 2 orders there for every selection. The question now arises, in how many ways can R objects be placed in different orders. Do you remember? It wasn't that long ago that we just had a look at this. Can you answer that question? Well, here it comes. Do you remember about this is given by the factorial, is the different orders? Remember this window? I said from 4 items, A, B, C, D, we could choose A, B, C, A, B, D, A, C, D, B, C, D. They are the 4 different ways you can choose students, a batch of 3 students from 4 students and 3 positions. And when we sat them down, we said we could distinguish which order they were in. So all of this becomes times by 6. Each one could be arranged in 6 different ways. And that was 3 factorial. In other words, if you're choosing 3 students from 4, there are the basic choices, the cross Lotto numbers, but then they were rearranged. So the product principle, or the permutation of 4 students taken 3 at a time, involves 3 factorial too many orders if you don't want to count them up as differently. So what would you do to the permutation formula to remove the different orders of the same R objects from N? Oh, are you good enough? Think about it while I roll the screen up and see if you can understand this. Uh-oh. Where did this come from? Just pause it and think about it. We've seen part of it before. Are you thinking? Right, we need to define a new term. Here's a new term to represent the selection of R from N, but where we just are interested in which R are chosen and not the different orders. So we have to wipe out the different orders of R items, and that's R factorial. And because each of the 3 students selected could be rearranged in 6 different ways, we've got to divide our permutation formula by R factorial. Okay, this wipes out those that are different orders, removes those of different order. Okay, because each selection up above could then be done around 6 times for different orders, or 3 factorial. So we need to remove that from the permutation formula. So that, do you realise that is the permutation formula, and there we are dividing by R factorial. Okay, so come on down, and we're nearly at the end. I'm glad that you stuck with it here. Okay, so it's called a combination, and you might have guessed this from up above where I said on the calculator you could do NCR. So you get the permutation formula and you wipe out the number of arrangements that are just different orders. So the permutation formula, and we're dividing by R factorial. I wonder if you are happy with that. See that? There's the permutation formula. And if we divide by R factorial, I wonder if you know that that pops into the bottom line. Well, let's put it over here so everybody can see it. So here it would be the permutation formula. Instead of putting that underneath and getting this confused big thing here, you could multiply by 1 on R factorial. Because if you halve something or divide something by 2, you times it by 1 on 2, don't you? So that means it drops down in the bottom line. Not everybody understands that when you are dividing a fraction by another number, it's the same as multiplying by the reciprocal. So that pops in there and removes the different orders. This is called the combination, not the permutation, the combination of n distinct objects taken R at a time. With the symbol CNR or on the calculator, it's that. It enables you to calculate the number of different ways you can choose R from N, but removing different orders as different possibilities. Because as with the cross Lotto, it doesn't matter the order in which the numbers come out. So you don't want to count all those up as different winning combinations. You have no chance of winning if you had to guess the order of the numbers as well. That'd be a lot of possibilities, wouldn't it? How many possibilities would it be? It would be, what, 6 factorial times as many, all the different orders. It'd be a lot bigger number. And here we are, advertising the graphics calculator again. You've got to have one of these, mate. Calculation involving combinations and permutations can be done with a graphics calculator. Run, options, probability, because it involves counting up all the possibilities, and choosing NCR or MPR, or you might want R factorial. That's in that window as well on all the calculators. Okay, so come down now. Here are some questions for you to try. In how many ways can a basketball club choose their committee of 3 from 50 members, so R is 3 and N is 50, if they're given the titles of President, Vice President and Secretary? This is very important. Okay, pause the presentation and have a go. Right, well, I hope you chose to write P53, or at least the box, which is 50, 49, 48. But I would like you to try to use that formula now. And if you did that and you multiplied all that out, you should have gotten 117,600. Okay, because we are counting all the different orders here. When we give them titles, it does matter whether you were voted in first. That was president, or you were voted in last. You were secretary, perhaps. You might want to be president. Doesn't matter whether you want to or not. It is a different arrangement if you're labelling the seats as next to the window or not. If I can just mix that in there a bit. Okay, so this would have been president, vice president, secretary sort of situation. So you looked at all the different arrangements of those. All right, so let's go down here now and let's see if you've got the whole message from this counting presentation. In the same club, so we've got 50 people, we're going to form 3, but they're all going to be just members of the same committee and not have different titles. I want you to pause the presentation now and see if you can work out the answer. All right, coming back now, I reckon I would like you to have thought of it like this. P53 divided by 3 factorial. In other words, realising because they're not given titles, we have to wipe out from these selections, this permutation of 50 people taken 3 at a time, we have to wipe out the number of orders. Or you could have said, there are no different titles, so I'm just looking at the selection or the combination of 50 people taken 3 at a time, realising that this doesn't count the orders, and that if you wanted to write down the mathematical formula, you could, like that, with that in the bottom, wipe out different orders, and then go to the calculator. Okay, you cannot use the box here because it contains all the orders. And so this is 19,600. Did you get it? And it, of course, is 6 times, or 1/6, sorry, the number of permutations, or the number of permutations is 6 times, or 3 factorial times 19,600. Are you getting up close and personal with this? Okay, let's come down for the last little bit here. So what is the answer to the cross Lotto question, finally? Well, the answer was, of course, we are taking 45 numbers in no specific order, not counting the orders as different possibilities, and we're taking them 6 at a time. And thank goodness we've developed our technique during this presentation, because the answer now is this. Do you want to play this game? I don't think so. That is the number of possibilities, 8,145,060. So you have 1 chance, if you choose 6 balls out of 45 numbers, of winning that game. Not very good odds. 1 chance in 8 million odd. Okay, have you enjoyed the presentation? I want you to think about the way of thinking that we have been doing here. We have been working on our ways of thinking about maths. And this is very important later on for problem solving. I want you to say, well, way back at the original window when we had all these symbols and stuff, it was quite surprising or even frightening But gee, I was able to think that through. And I might have gotten a headache at various times during this presentation, but that's what I want to do to develop my problem-solving skills. And I want to put in just a little ad for something I believe in a lot. You can use the rule now. You have lots of rules coming out of this presentation, but the idea of the presentation was to develop you as a mathematician and come up Huddy's hierarchy here. The rule, the concept, and now I hope you actually can say, when I read this in the textbook, I actually see it. I see what's going on. I am not going to stay at the base level. Not there. Don't stay there. Use the rule, but make sure you understand the concept and really get up close and personal with it. And so that's why this presentation was fairly challenging. But overall, take the challenge, get a headache, rewire your brain, develop your way of thinking. And I'll see you in a later presentation. Cheers for now.